Welcome back to another chemistry video. If you have missed this part in class, I will tell you this is a huge thing to know for the rest of the year. So get your PowerPoint out, make sure you're taking some notes, and make sure you master this. We are on Unit 3 right now, and Unit 3 kind of has a lot of stuff in it. We've got History of Atomic Research, which we're really not going to talk about on video. You can read that. And then today's topic, which is really the big part that I want you to start with, which is subatomic particles, okay? The things that make up an atom. Now, you guys have learned the structure of an atom zillions of times, okay? You've learned that there's a little nucleus in here, and you've learned that there are little clouds of electrons all around the nucleus. Worst drawing ever, okay? So hopefully at this point in your education, you know that an atom is made of protons, neutrons, and electrons. That's what I'm hoping is already tucked away somewhere. So today we're going to take that a little bit farther into how we're actually going to use that information. First things first, I'll tell you, sometimes protons are abbreviated with P with a little plus sign. Neutrons are sometimes abbreviated N with a little zero sign. And electrons are sometimes E with a negative. Why? Because protons have a positive charge, neutrons have no charge, and electrons have a negative charge. Hopefully you also know that your protons and your neutrons are found in here in the nucleus, and your electrons are found out here in what's called the electron cloud. So hopefully all that information is tucked away right now. The other little piece, though, that I want to add before we go on is talking about mass. Okay, we have this idea that an atom is these proportions that you're looking at in this picture. There's the nucleus in the middle, and then the electrons are pretty much the same size. Wrong. Okay, this nucleus by far has most of the mass. I mean by far. When you look at relative mass, because actual numbers don't mean anything, an electron is 1/1840th of a proton or a neutron. Okay, that means an electron is 1,840 times smaller than either a proton or a neutron. That's in terms of mass. Okay, your protons and your neutrons pretty much the same size. So the example that I've always seen before is if the nucleus was a soccer ball, okay, and we're holding the soccer ball in the middle of Stuart Straft High School, then your electron, your nearest electron, would be at Riverheads or at Amanda's Touch, if you know where that is. It would be 10 miles away, okay? If this nucleus were a marble, okay, a marble, then the surrounding atom would be the size of the football field. That's the kind of perspective you need for how tiny these electrons are compared to the protons and neutrons. Okay, so moving on here. We know all atoms have protons and electrons. For the record, most atoms have neutrons. The only one that doesn't is actually hydrogen. Hydrogen is literally just a proton and electron. But the big thing here you need to know is that elements differ based on their number of protons, period. Okay, it is possible for elements to have different number of electrons, but they don't have to. It is possible for elements to have different numbers of neutrons, but they don't have to. The one thing we know for sure is that elements differ based on their number of protons. So what we do is we give every element an atomic number. Now you have learned this in middle school, you may have reviewed it in biology, but this is not new information. Every element has an atomic number. Okay, that atomic number is the same no matter what atom of that element you're looking at. So when you look at a periodic table, hydrogen has an atomic number of 1. That means in every single hydrogen atom, there is 1 proton. Okay, the atomic number tells you how many protons there are. In fact, let's look at a periodic table. Okay, so periodic table here. Every atomic number, they're in different places on different periodic tables, but it's these little numbers up here in the corner. So those tell you the number of protons. So if you looked at cobalt, cobalt has 27 protons. Vanadium has 23. You don't have to know what any of these elements are, but if I say, hey, how many protons does silver have? You have to find silver, happens to be right there, and then you have to be able to say, oh look, the atomic number is 47, it's got 47 protons. Bam. Okay, in a neutral atom, and neutral is going to be where your protons and your electrons are equal. Protons are positive, electrons are negative, so if those two things are equal, then we know that we have a charge of 0. So, in a neutral atom, and everything we do for now is neutral, your atomic number can also tell you how many electrons. So in a neutral fluorine, there's 9 protons. That means there has to be 9 electrons, so we equal 0. Okay? Easy. Next number we're going to talk about is the mass number. Now the mass number is not found on the periodic table. And I'm telling you, you're going to try to go on the periodic table and find this. It's not there. The mass number is how many things are in the nucleus. So you're going to take your protons plus your neutrons, and that's going to give you your mass number. Okay? Now mass numbers can vary among atoms of an element. Okay? They're not always the same. Different elements can have the same number of mass numbers. Remember, the only thing that is specifically defining for an atom is its atomic number. So mass number is just how many particles are in the nucleus. So we use mass number with our atomic symbols, okay? You guys looked at the periodic table, you know every element has a symbol, okay? Sodium, for example, is not an S, it's an Na. Sulfur's an S. I'm not making you memorize the different symbols, but trust me, you're going to know the ones you use all the time. So when we have these symbols, they're not always straightforward just Na. Sometimes when you see them, whoopsies, what you see is Na, and it's got a number down here, okay, and it'll have another, sorry, that was the wrong one. Silly me, let me erase that. You'll see it with a number down here and another number up here, okay? These two numbers are not just random, they're there for a purpose. The bottom number is the atomic number, okay? So if that's Na, that's going to be an 11. This top number is the mass number, okay? That's protons plus neutrons. That's not always going to be 23. It is possible, for example, to have another kind of sodium, all right, which has got an 11 down here and a 24 up there. Remember, atomic number has to be the same, the others can vary. So the cool thing about these symbols is what we can find out, okay? I'm going to rewrite this one over here on the side for you. There we go. So let's say I wanted to know the atomic number, if that was all you were given. Well, that's easy enough. The atomic number is 11. Now let's say I want to know the mass number. Easy enough. It's always on the top. That number is going to be 24. Well, now I can get crazy smart. How many protons does this guy have? Well, okay, atomic number is 11, so it's going to have 11 protons. How many neutrons does it have? Well, mass number is protons plus neutrons. So 11 plus something has to equal 24. Well, that something has to be 13. How many electrons does it have? Well, if it's neutral, my protons and my electrons have to be the same, and we know that it's neutral. We're not dealing with anything else yet, so that's going to be 11. You can gain a lot of information from these symbols. All right, let's look at another one. Let's look at BR 8035. Okay, again, I'm going to make really quick abbreviations just so this doesn't take as long. What's the atomic number? Good, atomic number is 35. What's the mass number? Mass number is up top, that's 80. Now let's look at subatomic particles. Protons is the same as the atomic number, so that one's going to be 35. Electrons, okay, electrons if in a neutral atom, and again, everything we're dealing with right now is neutral, are going to be the same as protons, so that's easy. Neutrons, again, this number right here, this mass number, is protons plus neutrons. So I know I have 35 plus something has to equal 80, so I got to do a little math. Yes, you can use a calculator, and I will get 45 neutrons. Okay, so those are your symbols, all right? The reason we care about all of these symbols is because, I've said this before, not everything is the same. Just because it's the same element, it's not the exact same atom. There's something called isotopes, all right? Isotopes have the same number of protons, so they are the same element. I mean, it's sodium, it's carbon, it's the same thing, but they will have a different number of neutrons. Okay, that's what an isotope is. Same number, same element, so same number of protons, but different numbers of neutrons. So your mass numbers are going to be different. So we can have helium. Okay, helium has an atomic number of 2. That doesn't change. But we can have helium with a mass number of 3 and helium with a mass number of 4. Okay, and the way that we name them, so we don't have to draw these symbols all the time, is we name them based on their mass numbers, not math. So this, for example, is helium-3. This is helium, wait for it, 4. So you write the name, a dash, and then the mass number. Okay, and then we can put everything back together again. You got a sample problem in your PowerPoint. It says the atomic number, okay, atomic number is 34, and the mass number is 78. So we're going to play Name That Element. Yay! So first of all, how many protons do we have? Well, if the atomic number is 34, how many protons do we have? 34. Neutrons. Okay, we know that protons plus neutrons equals the mass number, so we got to do a little subtraction here. We have 44 neutrons. Okay, how many electrons? Well, everything we're dealing with now is neutral, so that's easy enough. Got to be same as the protons. Now let's look at the symbol. Okay, to find the symbol, we know that we're going to have an atomic number down here, and we're going to have a mass number up top, 78, but I got to figure out which element this is. So what do? I go to my handy-dandy periodic table. Looking at the periodic table, I'm looking for element number 34. So I buzz on down, there's element number 34. It is selenium. Okay, so I'm going to go back over here and finish my symbol. All right, that is my complete symbol for this element. When I name it, I'm not just going to say, oh, it's selenium, because there's multiple kinds of selenium. There are different isotopes. I'm going to say it's selenium-78. Okay, that takes a little practice. You got a couple more practices in your PowerPoint, plus you actually will have a whole bunch of practices on a worksheet once you're back to school. So let me add one more piece onto the puzzle. We've done atomic number, we've done mass number. The next thing we have to talk about is atomic mass. Yes, it's annoying that all of these things sound alike, all right? I'm sorry, there's nothing I can do about it. The thing with atomic mass is we don't want to put mass numbers for every single thing on the periodic table. Some of these elements have 5 different isotopes. Can you imagine 5 different mass numbers shoved in those little squares? That would be confusing. But we also can't look at the mass when there's 5 different isotopes. Like, how could I tell you what the mass of carbon is, for example, when some of the carbon, okay, is carbon 12. There's 12 things in the nucleus. Some of it is carbon 14. There's 14 things in the nucleus. This one has a far greater mass than this one. So when I want to tell you how much this thing's mass is, it's not really that easy. So the way that scientists have devised to do this is they actually just use an average. But it's not a 50-50 average. It's based on the abundance of these things in nature, meaning how much of each of these are there, okay? And we use a special unit called an atomic mass unit. So let me leave atoms for a second and come back to this abundance thing using rocks. Great example in your PowerPoint. Let's say you have 5 rocks, okay? 4 of them have a mass of 50 grams each, okay? And then 1 of them has a mass of 60. If I want to know the average mass of the rocks, what is it? Okay, most of you guys did not say 55. You're not just going to say, well, I don't care that there's 4 of those and 1 of those. I'm just going to average these numbers together. Of course you're not going to do that, okay? You're going to say, okay, I got 4 of them that are 50 each, so 50 plus 50 plus 50 plus 50, and then 1 of them that's 60 each, so I'm going to add all that together. I'm going to divide it by how many rocks I have. That's 5. So my average is going to be 52 grams, right? Okay, that's really what you're doing with elements, except we're looking at percentages. Okay, now again, we're going to say you have rocks, but this time we're going to say you have a bag of rocks. 80% of the rocks in your bag have a mass of 40 grams. Now this is different than the last problem. Okay, 20% of the rocks in your bag have a mass of 30. What's the average? Okay, this is where a lot of you guys are like, I don't know. You know kind of what to do, and some of you can instinctively figure it out. Others of you want a formula. I'm going to tell you right now, if you can instinctively figure this out, do it. Okay, ignore the formula I'm about to teach you because it's going to be the same thing you already did. People do this different ways, all right? But I'm going to give you a formula, so if you're not much of a math thinker, okay, you don't think through things like this and you just want your formula, I'm going to give you your formula. So here it is, okay? To calculate average atomic mass, you are going to take for each isotope a set of parentheses. So if there's 2 isotopes, you have 2 parentheses. If there's 3 isotopes, you have 3 parentheses, etc., etc. And in each set of parentheses for that isotope, you're going to take the percent as a decimal and multiply it by the mass of that isotope. Okay, so each isotope is different. So percent as a decimal times the mass of this one. Percent as a decimal times the mass of this one. Okay, however many isotopes you have, that's how many sets of parentheses. It can be 2, it can be 5, it can be 7. I'll try not to go there very much. So here's a sample problem. Okay, we're going to look at copper. So the deal with copper is 69.1% of copper has a mass of 62.93 AMUs. Okay, 69.1% is a mass of 62.93 AMUs. The rest of copper on planet Earth has a mass of 64.93 AMUs. Okay, so again, some of you guys can instinctively figure this out. Beautiful. But if you can't, don't. All right, so what we're going to do here is we're going to use our formula. All right, we have 2 different isotopes in this one, so I know that I need 2 sets of parentheses. Okay, so first what I'm going to do, the percent as a decimal times the mass. So percent as a decimal always goes back 2 decimal places. So 69.1% becomes 0.691. Percent signs are a pain to use in a calculator, so we make them into a decimal, makes our life easier. And then we're going to multiply it by our mass, which is 62.93. Okay, then we've got to do the rest. Okay, well, how do you turn the rest and do you move it back so the decimal's between the R and the E and the... No! What you have to do is figure if you have percentages, they always add up to 100. So if I know 69.1% is taken, okay, I'm going to subtract that from 100 to figure out what the rest is. Okay, and I'm going to end up with 30.9%. All right, so I'm going to change that into a decimal, 0.309. And then multiply it times the mass of that isotope, which is 64.93. Now, some of you are going to want to divide this by 2. Don't. We're not doing an average in that way. Because we're using these percentages, there is no more step. This is literally all you have to do. And when you solve this, you will get 63.55 AMU. That is the average mass of all the copper on the planet. Okay, we've literally taken every little piece of copper and we've massed it out and we've averaged it. There it is in 2 simple steps. Okay, so we'll be back next video. We'll talk about some moles and some other cool things. But for now, practice your subatomic particles, practice your isotope notation, and then practice your average atomic mass. See you next time.